This is lesson 5 in the quantitative chemistry section. This lesson is about something called a mole, which is not a small furry thing that lives in the ground, at least not for a chemist. A chemist is a unit. To a chemist, it's a unit, and we use it to count numbers of atoms. Okay, so we're going to be able to state that it's a way of counting atoms. We're going to calculate the mass of a mole of a substance, and we're going to explain that the mole always contains the same number of particles. Be very careful, okay? I'm going to explain a little bit more detail. So I guess the thing I want you to think about is how much atoms weigh. So if you think back to what you've learned about atoms so far, you learned there's a small nucleus with some protons and neutrons in there that have a very tiny mass, and then you've got electrons going around the outside which have even smaller mass. So how much will an atom weigh? So you should remember from year 9 that atoms are really, really small. So here I've got this atom on this little picture here, and if you think back to your electronic configuration lessons, you should even be able to work out what that is. It's got 2 protons in the nucleus, and so 2 protons, you look for number 2 on your periodic table, and you find it's 42He. Okay, so it's got 2 protons in the nucleus, 2 neutrons in the nucleus, and 2 electrons going around the outside. So I've got the mass for hydrogen in kilograms, so it will be, right, the mass of hydrogen in kilograms, just to give you an idea of how tiny it is. It's 1.67 times 10 to the minus 27 kilograms. So that's the mass of a hydrogen atom. For those of you working at a higher level, remember that hydrogen is 1H. Mass of a helium atom is actually going to be 4 times as big as this. Don't worry if you don't get that. But basically, the real thing I want you to understand is that they are super tiny, really, really small. And I sort of sat down and worked out, looking at the distance, there's the radius of an atom as well. Okay, so 25 picometers. And if there's a piece of paper that is 0.1 millimeter thick, you could theoretically fit 4 million of them side by side on the edge of a piece of paper. Okay, so on the little tiny edge of a piece of paper. So very, very, very small indeed. So we use the mole to count atoms, as I said, because we can't look at the mass of one atom. That little diagram on the last page showed you a little chap measuring things out with tweezers. Obviously, we can't do that. So we look for a certain number of atoms. We look for 6 times 10 to the 23 atoms. Okay, or 6 times 10 to the 23 particles, I should say. I'm going to be very clear about that in a minute. And this is a mole. Okay, so it's like saying that a dozen is 12. Okay, it's exactly the same concept. You've been happy to call 12 things a dozen since you were a little kid. So just new idea is that 6 times 10 to the 23 of something is a mole of something. So you could have a mole of cups. There'd be 6 times 10 to the 23 cups. It'd probably take over the whole of the earth. A mole of moles. You could have a mole of anything theoretically, but we use it to count atoms. So here's the rule that you are going to have to learn, and that will start to make more sense as you use this. Okay, so 1 mole of carbon atoms has a mass of 12 grams. Okay, that's what I'm looking at this bit here. Okay, 1 mole of sulfur atoms has a mass of 32 grams. 1 mole of hydrogen molecules has a mass of 2 grams. Now, where are those numbers coming from? Now, some of you who have switched on and have seen your periodic table might think, hang on a moment, carbon. I remember there's something about 12 and carbon. So this is where we're going to go next. So this is the symbol for carbon, and its relative molecular mass and its relative atomic mass. Okay, and you see that each carbon atom has 12 fundamental particles. By that I mean it's got 12 protons plus neutrons. Okay, so we basically have set this magical 6 times 10 to the 23 number to match up with what's going on in the periodic table. So I just talked about the fact that 6 times 10 to the 23 matches up with the number in the periodic table. So this is the rule you're going to have to learn, that the mass of 1 mole of a substance is always equal to its relative formula mass. Okay, so if you crack this idea and we understand what that means, we will always be able to measure, give the mass of 1 mole of a substance. Okay, so mass of one mole of substance is always equal to its relative formula mass. So for carbon goes around as individual atoms. Okay, well, you know a little bit more than that actually now. You know it's a giant macromolecular structure, but its simplest formula unit is just one carbon atom. It's not a diatomic molecule like oxygen, or it's not an 8 ring like sulfur, okay? So its simplest formula unit is just C, okay? So we set the mass of 1 mole of carbon equals 12. Okay, but remember that not everything goes round as atoms. Remember that oxygen, so 16,8 oxygen, goes round as O2 molecules. Okay, so the mass of 1 mole of O2 molecules is going to be 16 plus 16, which equals 32 grams. Okay, so that comes from each atom will weigh 16. Okay. The example I've given here, the mass of 1 mole of carbon dioxide is 12 for carbon, plus 2 times 16, and add that all together is 44. If you want to work out, cool, let's have a look at sulfur. Keep talking about that. And it actually exists as S8 rings. Okay, so the mass of 1 mole of S8 molecules will be 32 times 8. Okay. Another example. Okay, so let's do 23Na, 2311Na. The mass of 1 mole of sodium atoms will be 23 grams. Okay, so you can keep doing this. You can do this even with quite complicated things. You can go for copper sulfate dot 5H2O. Okay, so you can add the mass of copper, 63.5, plus sulfur, 32, plus 4 times 16, plus 5. Right, what this means is 5H2O. This is definitely for you higher level students. It means there are 5 molecules of water in the crystal. Okay, so you have to have 5 times the 18 for H2O. So this comes out at 249.5. Don't ask me why I can remember that number. Grams. That's the mass of 1 mole of copper sulfate. So we have a formula triangle to help you with this. Okay, it's the idea, it's the way that we relate mass, moles, and formula or atomic mass. Okay, so remembering how you use one of these formula triangles, if I'm trying to calculate the mass of 1 mole, okay, so my mass will equal my number of moles multiplied by my relative formula mass, which is what I was just doing there, adding up the numbers from the periodic table. If I'm trying to find the number of moles present, so let's say I've been given a sample of 10 grams of carbon and I want to know how many moles of carbon is that. So again, I cover up my moles, okay, I say moles equals mass divided by my relative formula mass. So in this case it would be 10 grams divided by 12, okay, so 5/6 of a mole. And then you can also solve for relative formula mass. That's something you want to do more at A level. Now you can remember the formula triangle, but a nice way to remember it is that a lot of people also remember this called mass equals Mr. Mole, okay, so this is Mr. Mole here, and the mass is the MR, which is what I've been describing to you as the relative formula mass. It's just another way of writing the relative formula mass. You can call it MR, okay? And the moles are the number of moles, obviously. So whichever way helps you to remember the equation. So this is the point I wanted to be making right since the beginning of this PowerPoint. I'm going to labour it one more time for you. Remember how many? We said a mole is 6 times 10 to the 23. Oops. Particles. So, how many atoms in a mole of carbon? There are 6 times 10 to the 23 atoms. How many water molecules in a mole of water? 6 times 10 to the 23 molecules of H2O. how many pairs of ions in 1 mole of salt, let's say sodium chloride, it would be 6 times 10 to the 23 pairs of NaCl in 1 mole of a salt. So the key idea is that the mole is the number of particles. Okay, so you need to think about what kind of particle is there. Okay, so is it an atom? So are you looking at like something like a metal or carbon or perhaps a noble gas? Are you looking at a molecule instead? Are you looking at oxygen or water? In which case you need to calculate the mass of one individual molecule to give you the mass of 1 mole of those particles. Or is it an ionic substance? Here we go, going over one more time, okay? So a mole of carbon atoms has 6 times 10 to the 23 carbon atoms and it weighs 12 grams. A mole of hydrogen molecules contains 6 times 10 to the 23 hydrogen molecules and it weighs 2 grams because each hydrogen atom, okay, weighs 1. So 1 plus 1 is 2. There we go, so we get it from methanol. So you might not know the formula for this, which is CH3OH. Okay, so 6 times 10 to the 23 methanol molecules in a mole. So you'll do that, you work that out by saying you've got 12 for carbon, plus 3 times 1 for hydrogen, plus 16, plus 1. Okay, and that comes out at 32. Well, there's a lovely little section of my ionic lattice here, 6 times 10 to the 23 pairs of sodium chloride ions. Sorry, that should be in standard form. And as I said to you, the idea that you can use a mole to count anything really, I suppose. And I had this thought about if you had a mole of sheets of paper, if you had 6 times 10 to the 23 sheets of paper, and I measured that about 500 sheets, which is a ream where it is about 5 centimetres thick. So it's an awful big number, a mole, 6 times 10 to the 23. It's almost impossible for us to imagine. If you had that many sheets of paper piled on top of each other, it comes out at being 6 times 10 to the 20, let me write this down properly, 6 times 10 to the 16 kilometres tall, that pile of sheets of paper, which I worked out, I may have got this wrong, but I think it says 750 times to Alpha Centauri and back, which is not quite our nearest star, it's the nearest but one. So 6 times 10 to the 23 is really an awfully big number, and the weird thing about it is that you can drink a mole of water atoms quite easily in a glass. So very, very big number. Atoms are very small.